So do you remember that when we started the Kalman filter has the specific assumption, you see it's here, yes. We have the specific assumption about the Kalman filter. The assumptions are the following. I have the update of the state, and the update of the state, or the set of states, it happens because I have a recursive relationship where I know the transformation, linear transformation A, and I have the injection here of the excitation. So if I break this point and I let it go, this guy keeps going autonomously, okay? Anyway, but this is a model of the system. On the other hand, we cannot observe directly theta, but we can observe theta through another transformation. And this additional transformation, which gives me x, now x is out of the shaded area, which means x is the only I can see. Okay? I don't see the others. Okay? And so from x, my goal is to infer the property of theta. And by knowing that theta is recursively updated according to a relationship which is known, A, but not with the excitation, random excitation alpha, then my goal is to put in chain, which means to put together one after the other, all my observation x in such a way that I can track all the parameter theta. Now, if alpha is Gaussian, if beta is Gaussian, as it is for Kalman, this means that regardless of my initial condition, I keep on circulating random variables that ultimately they are Gaussian by the central limit. Okay? So that means that everything here is Gaussian. So theta is Gaussian, this is linear, so theta Gaussian, alpha Gaussian here. And then I have a transformation of Gaussians, so that means that x is Gaussian. So, if we go back to our theory, we saw that if I have random variables that are jointly Gaussian, which means theta is Gaussian, x is Gaussian, then the optimal estimator is linear. Okay? So the Kalman filter is the optimal estimator in this condition. But, in addition to that, is the optimum tracking filter, which means it can optimally estimate the sequence of states, which is different from estimating the state, which is a parameter. I'm estimating the sequence of states. So this is the reason for the meaning tracking. Now, when everything is Gaussian, so if what I want to estimate is the a posteriori probability of theta. But now, we are essentially in a Gaussian distribution setting. And so that means that if we want to calculate the Gaussian, so we need to establish the first two moments. So the mean and covariance, okay? So once we know the mean and covariance, that means that we know the distributions. So our Kalman filter is essentially the relationship which is updating the mean and covariances either a priori and a posteriori. So seen in this way, then that means that my updating and correcting, so my predicting and correcting formulas should contain these relationships. What we found, and what we derived, here, and we go to the yeah. What we found that since everything is Gaussian, then the mean coincide with the estimate. So then we have in the prediction mode, that means that we are predicting. Now look at here, in the prediction mode I'm not using the data. Okay? So I know the a posteriori at a position, at the time n-1, and then by transforming according to the linear relationship, which is A matrix, and I get the theta hat n, which is the predicted value at the time n. Similarly as with the mean, I can update the covariance. So this is the mean and this is the covariance for calculating from the a posteriori to get the a priori. Then once I have the new data, which is xn, you see I don't have xn. So when I have the new data, I can calculate the new a posteriori. And the new a posteriori at the time n, which means is collecting all the samples up to n, is obtained by taking the predicted value, which is here, the predicted value, and then I is multiplied by a gain, this is a common filter gain, time the prediction error. The prediction error is calculated at the time n using all the prediction coming from n minus 1. The gamma filter gain is quite expensive to compute. Similarly, as I calculate the mean, I need to calculate the covariance. Okay? And then I continue with that. So looking at the corresponding code, it's pretty complex. Okay, as usual. Okay, all we do is very complex in terms of code. Okay? Now, and I mentioned you a little bit some of these properties in the last time. So let's start with the one example. Okay? So what I'm going to do today is, even if for you it seems new stuff, but it's just examples. Now, example number one is more telecom oriented. Now, for non-telecom, let me say what's happening here. Now, on this side, this guy is transmitting bits. Okay, from talking for a non-telecom. So this guy here is transmitting bits. These bits that are, visually, you transmit one rectangle on the air. Okay, you need to see this rectangle which is traveling over the air. Now, this rectangle is bouncing on some obstacle, and then after bouncing, it goes to this receiving device. So this receiver, this guy, okay, which is traveling on a car at a certain speed, e, then what's happening is also affected the receiving signal by the noise coming from other transmitters. Okay. Now my received signal is bouncing on wherever, and is not received by the direct line, the line of sight. Okay, which is the line where the visibility line between transmitter and receiver. Okay, because there are obstacles, whatever obstacle is there. Okay? So now, all these devices means that when I receive my rectangle here, it's not a very nice and clean rectangle, because each of these arrays has a different delay. So I have one array which has the first delay, the second array which has another delay, the third array which has another delay as well. So what you have a composition, you can see it, is a composition of delayed waveform. So you have a first one, then you have another one which is perhaps attenuated, then with the delay you have another one. Okay? So what you receive is a superposition of these ones. And this superposition is the black line there. Okay? Of course, this is what's happened with the 1 bit. And the telecom, they survive all the life knowing that everything happens in 1 bit, it happens in a sequence of bits, because the system is linear. Okay? So once I study what's happening in 1 bit, I know everything about the other bits. Okay? So now and by the way, all the algorithms that has to do with this simple problem, and when the problem. So let's make some advertisement. So everything that has to do with this simple problem, or when the number of antennas is many here, and when the number of antennas on the moving device is many, is several. That is a MIMO, by the homework number 1. And when this guy is moving, it's a MIMO with a time varying propagation setting. And when it moves, you probably remember by physics that you have a Doppler effect. Okay? So all these problems, which is a key problem for telecom environment, but all these problems, it contains a lot of statistics, enormous statistics, and there is a very huge amount of smart algorithms that has been derived by putting together algebra, statistics, mathematics, and so on. Okay, so this is an area where, in case you are working in this area, it's not just a telecom. And most of the telecom students, they look at this, but they forget. Okay, so you need to work on this topic specifically in order to develop the algorithm related here. That means that if you want to work in this area, working on how to handle the signals here, you need to be strong in algebra and mathematics. Okay? Algebra, mathematics, and statistics. This comes first. Now, going to the point. For this simple problem where I have one transmitter and one receiver, okay, then what's happening is that, I transmit a picture and then I get a distorted one. That's my thought, right? So, so the waveform here that I transmit, it comes to this one that is distorted, you see, okay? Now, these communication system can be fully equivalent to the following discrete time system, where the discrete time system contains, as input, I have the bits, actually the value of the bits, or, they have a symbols. So symbols means that, the input A, N, is belonging to a finite difference alphabet that you probably saw, in homework 2. And so this alphabet, it might be an alphabet that contains, for instance, a plus minus 1, plus minus 3, for instance, and so on. Okay? It depends. It depends, what kind of things we are dealing with. So that is a finite difference alphabet. And of course, this finite difference alphabet is related to a set of bits that you want to transmit. Now, going to the other side, this is propagating through a linear time invariant filter. Actually, it's not a time invariant because this channel is changing because the vehicle is moving. So when the vehicle is moving, age is not really time invariant. Okay, but so it's a linear filter. Let me say for a very limited time is time invariant. And this noise is coming as an interference. So this interference models as Wn, and then what I receive is Xn. Okay? So, every time you see a data communication, every time you see a data transmission, every time you see a mobile phone using Wi-Fi and so on, it uses this model. Okay? And the people who have developed any algorithm has been using this stupid model. So that means that, we need to study it a bit. Now, let's move a little bit forward. So, as I told you, by the way, this guy is called the channel, but channel is a jargon for telecommunication. So, that's a filter, okay? So, let's call it filter. Now, if you are a telecom, you call a channel, but it doesn't matter. So, that's a filter. So, now, what has this filter as a peculiarity? Now, this filter is time varying, okay? So it's time varying, you see here. That means that it's time varying because the vehicles are moving. So that means that the output Y, I change the notation. Okay, I change the notation. So the output, I don't know about the book probably. So now, the output Y, which is the output of this communication chain, is equal to the H, K, convolved with X n minus K. But now So this is the relationship of convolution. But this filter is time varying. So since it's time varying, it depends on n, the index n. Okay? So you know, technically, I mean, even if it looks like a convolution, it's a convolution only if the variation of the filter is very slow. Now, rephrasing everything into a block type, block time processing, I have that the block of the vector or the segmentation of the input x, which is indicated as xn, is multiplied by hn. Now hn is the filter. That is time varying. Okay, plus w. So, you know, my assumption, the assumption I made is that h, the filter, is causal, which is not true. It's true for physical reason, but you know, it's not true in processing. Let me tell you the reason for that, you know, okay? Because you might be surprised. When I transmit the bit goes to the receiver. The receiver doesn't know the time when the bit was transmitted. Okay? So there is a propagation between. So if I send you a pulse and you receive a pulse, which is a bit, and when you receive the bit, you know, you try to recover, try to understand when the bit was transmitted. What you say is that the bit is transmitted when you see the bit, you know, going up. Okay? Now, this is the easy part. But you know, if I tell you this signal here, which is going strangely this way, and I ask you when this strange convolution of the pulse with the corresponding propagation environment, when this guy was transmitted. Well, I can say that it was transmitted here, but you know, it might be transmitted there. So this has following a shortest path. So since the receiver, so you know, the guy here that is observing the signature has to establish the timing of the corresponding communication part. Then for this reason, the receiver might set the transmission point wherever is more convenient. And so one common way is to set the timing according to the body center of the waveform. Which means that if I put this timing here at 0, so for me here is 0, then this is anticausal, this is causal. Okay? So it's a part of the technicality, how the communication is carried out. And on the other hand, you know, if you look at a movie on the TV, and you know, if the movie has a delay of 1 second, do you realize? No, right? Okay, so no, if you look at whatever movie or whatever music or whatever, okay, and you have no feedback, you never realize when it was the origin time, when it was the time 0. And so you arbitrarily say that the time 0 is referred to any arbitrary point according to your local, let me say, it's a local physiological estimate. So, you know, according to that, then, I mean, this is the reason why the filter might be causal and anticausal. And other reasons that telephone knows. Okay, now, so this is the filter. So my goal is to estimate the filter. Now, so this filter response, which is varying in time, is my unknown. Now, so far, it would be a problem similar to the others. But what makes the problem different here is that the filter is changing according to a load, which we know. So this is totally new. So seen in this way, without any auxiliary equation, we have the output equal to the input convolved by the filter plus the noise. So if my goal is to estimate the filter, for instance, which is the system identification, if I know X, which is a training sequence, as is in the homework, Okay? If I know x, then I can estimate h. But you know, the new part is that h is varying. Now, if the variation of h is known by the estimator, and if the law of the variation is known by the estimator, then I can include the law of the variation into a set of equations. So, put another way, that means that I have the training with a known sequence, which is a set of training, and this is the equation that I was describing, okay, where this one is the training. And I know the dynamic evolution of the state, which means, I know how the channel is varying in time. I don't know exactly. I know with some uncertainty. And my uncertainty is established by an excitation part, which is V. So what I say is that the filter response at the time n is the filter response at the time n minus 1 multiplied by a certain matrix plus Vn, where Vn is a random term, is an excitation part. Okay? So, so far, put in this way, with this one, which is H is a state, and then, A is a matrix which is making the state evolving. V, which is the fluctuation of the channel of the filter, okay, is a random part. And then Y is what I measure. Convolve, so which is a convolution of the channel time of training plus the noise. In this setting, the problem is framed as a Kahneman filter. Because, the state, H is the state now, okay? So, this is the relationship on the evolution of H, okay? Which is how H is evolving. And I know A. And this one is let me say, state to output relationship. Then these two are the two equations of the Kahneman filter. So I can implement the Kahneman filter here. Now let's add a few comments on this. Now these comments come from the physical meaning of all the quantities that are indicated here. Now, a common way to consider H is by considering that H is varying according to like a Markov model chain, which is a recursive. Okay, so which means I can say that H is equal to a scaling factor of H n minus 1 plus the excitation. So looking at this way, I have H and 1 and A2 and H V and okay. This is the vector H n. So each of these is equal to rho times H1 n minus 1 and so forth. Okay. So this means that H I n is equal to H I n minus 1 multiplied by rho factor plus I have a V. I have a VI. VI is a random, it's an excitation part. So looking at this equation is the equation which is representing autoregressive behavior for H. So H is behaving as an autoregressive random process. So H is changing, and according to the value of rho, if rho is very big, then what's happening is that the samples of the filter response are highly correlated. If rho is very small, then they decorrelate very quickly. Now, furthermore, we can assume that X, the training sequence, is ideal. So we can assume that the training sequence is known to the transmitter and receiver. Now the transmitter and receiver know the training sequence Xn, and then we can assume that Xn is drawn, taken from a random sequence, which is known to the transmitter and to the receiver. Okay, so transmitter, receiver both know the training sequence, which is similar as you did in, for sure, with Matera. Okay, the exercise you did with Matera by MATLAB. So it's in this setting, if X is random, but known to the transmitter and to the receiver. So if this training sequence is known to the receiver, to the transmitter and receiver, then I can assume that this training sequence is drawn by random samples that are independent and identically distributed. Independent means the samples are independent, statistically independent of one another, and identically distributed because the samples are drawn by the same distribution type. So in this case, we can assume I'm putting all the assumptions. So in engineering we don't put assumption. Okay, the assumption comes from the physics. Okay. Now, so it's because of that. So the training sequence of random variable samples uncorrelated one another, uncorrelated Gaussian. Okay. But usually they are statistically independent. But we have that these training sequences are characterized by having a correlation matrix that is identical, scale identical. Now we can implement it to Kalman filter on that. And so we don't have new slides, but we can implement the Kalman filter because we have all the assumptions. Okay. And then, so we can implement the Kalman filter to track the variation of the channel according to the property of the matrix A. Now, let me add another comment. I write here. Let me add another comment. Now, this comment is mostly for our telecom colleague. So, A matrix. If I write A matrix as a row time identity, okay, which implies that it has, I wrote here, HA at time n is equal to H row time H A at the time n minus 1 plus V n. Okay, now, rho, okay, which is a correlation factor. Okay, which means that the autocorrelation of H K, okay, is behaving as rho to the power of K divided by 1 minus rho square multiplied by sigma square V because it's autoregressive. This is the property of the matrix H. Now, rho is a correlation factor. Rho depends on the speed. Okay, so rho depends on vehicle speed. So if the speed is low, then rho is close to 1, which means the filter is decorrelating very slowly. Okay, which means it remains the same all one sample after the other, which means that the is approximately static. Okay, which means that in this case our mean square error will be the best because the channel doesn't move much. If the speed is high, I'm not saying how much high because it depends on the setting of the problem, then a rho is lower than 1, then the filter is fast varying. Now, that means that there is a relationship which I'm not mentioning, is that the rho is a function of the speed. Okay? Now, in other setting, in other context, we might use an autoregressive order 2. So if I'm using autoregressive order 2 for the filter, which is as well typical, okay, that means that I can manipulate my relationship to put in such a way that they can be written according to the state equation. Okay, this is one example. So one possible example, one possible application about the Kalman filter for tracking the filter response in a communication system. Now let's move to another application. Let's consider the application of position. We started talking about tracking by looking at the position. Okay. So how is carried out the position? Now, in order to simplify, in the book I use the fact that the problem is bidimensional, even if the GPS positioning is three-dimensional. Okay. So to simplify, let me say I have a set of transmitters or receivers. Okay. Actually, if I am mimicking the GPS, these are transmitters. So remember, in GPS, my satellites are flying. So everything I'm saying, is in three dimensions. Okay? I'm not putting the problem that way because there is a curvature of the Earth, satellite, blah blah blah. Okay, so everything makes a little bit more more involved because of the geometry of the setting. But the conceptual part. So let's consider the case where we have a set of stations, let's say Rn, and I have one devices which is in the position Rx and Ryn. The devices is moving. Okay. Now what's happened is the following: if I receive, or there is a certain propagation delay between the station and the device, then I can measure this delay, and according to this delay, I can find the locus of the point where the device is going to be. So if I have a certain delay, the device is going to be within this circle that has a radius that depends on the propagation time. So if I have, if I measure the delay between the station number 1, which is geometrically positioned in a plane in a position Rx1, Ry1, then I measure the delay tau 1, and then I get R1, which is the distance between the device. The device can be a phone, just to say. So it's the distance between the device and the station. So from tau 1 and I get R1. So tau 1 is the time of delay. So from the time of delay tau 1, I get the distance R1, and similarly for the others. So the position of the target, okay, which is the point that I need to position, is localized as a crossing point from all the isotime, which is the locus of the same time. And due to the geometry or the characteristic of the problem, all the isotime is circles. And so the circles crosses into the point. Okay? This happens, in an ideal setting. Furthermore, the point moves. Okay? So the point, is Rx and minus 1, Ry and minus 1, Rx and Ry and so on. Moving across the space. Now it can be, okay, this area is called service area, just to put some jargon on top on that. And the positioning problem is not only by GPS, but there was and there is a strong interest to establish the position by using the active communication systems. And the reason is very simple. The GPS is working because I have a visibility with the satellite system. And if I am indoor, there is no satellite. So indoor, across a tunnel, there is no satellite coverage. And so there is no possibility to get the position. So there is a strong discontinuity in positioning between outdoor, where I can listen to the satellite, and indoor, where I cannot listen to the satellite. Second, the satellite might be turned off. So if it's for some reason the satellite is turned off, then all the traffic is stopping, okay? So even if in some cases the very easy solution would be that I can localize by the satellite, but in practice I cannot rely on satellite because the satellite is, for instance, GPS is owned by U.S. Army, and Galileo is a civil one, which is it's a European one, and so there is all these issues, okay. So this is the reason why, for instance, a railway network is never localized by the satellite. Okay, they are localized by a specific localization strategy. Okay, which is different from the satellite. They don't use the satellite, for instance. So, according to that, you need to see that the two-dimensional system that I am illustrating here might phase for these transmitters as transmitters due to the cellular networks and or other devices. Okay, so this bidimensional system that I'm illustrating here is not so crazy. Okay, so it might be feasible because it is illustrating something that exists. Now, how many transmitters do I need to localize a point? Now, I need at least 3 transmitters, and they should not be aligned. In other words, if I take, for those of you that makes the example with Professor Nicolai, probably they know all about that. But if you have a point here, which is you, and you have your own device, and if the three transmitters are positioned all along the line, so all the circles, they cross in this point, okay? Now, they cross in this point, but the uncertainty where they cross is very huge. Because, these time, so remember, I got a time n, tau 1, and then from tau 1 I got R1n. So on the time from delay, I got the radius, okay, it's called range. In jargon it's called range, but the distance. Huh? So from the time delay I got a range, but the time delay is never estimated with accuracy, with infinite accuracy. So because of that, that means that this radius has a certain, let me say, let's put it as a Gaussian uncertainty. So that means that this radius, which is the range, has this degree of uncertainty. Okay? Then I take another one. So the second one has the same uncertainty. Then I have the third one, and this is second uncertainty. So, intuitively, all the crossing of all these uncertainty makes this point to be localized in this region. But that means that I am quite accurate to estimate the position of the point in radial direction and very poor in the other direction. Okay? So, but the minimum is 3 because, and the optimum would be if I put the 3 transmitters at the vertex of a triangle. Because in this case, assume that you are at the center here. So that means that every distance that I measure between the target and this station, which is this corner, the locus is a circle. Then the locus there is another circle, and then the third locus is another circle. Okay. So even if the circles crosses in this point, but they all crosses in one point, and then we colocalize. Now, even if each of these radius estimate is estimated with an uncertainty, we can see that all these uncertainty region now is more isotropic than there, is more circular. Okay? So this uncertainty, which is very spread in that direction, is worse than this uncertainty that is approximately circular. If you see the code, okay, the code GPS on your cellular phone, where the system is positioned yourself, and you see these circles that are shrinking and squeezing and enlarging, and this is due to the fact that you are measuring more or less satellite or other devices that you integrate to calculate your position. Now, this is another reason why the satellites are spread out, and you hope, and you know what you want. You want to see the satellites that are angularly positioned, angularly far away one from another, in such a way that if they are angularly far away one another, I get my uncertainty region that is very broad. Now, anyway, so going to the point, going here, so I receive, okay, so I put as if, to simplify, I put as if, this device transmits a signal that is received by all the stations, even if in GPS it happens the opposite, okay? It's the station that are transmitting the signal to the device. But I simplified further the model. So in my model, this guy is transmitting a signal that is G of t. And so here I receive G of t minus tau 1 plus naught. Okay, this is what I receive every station. Now, okay, this illustrates, what I was saying about the uncertainty. Okay, so if every measurement is affected by an error, the error is in solid. With respect to the idea is in dashed. So what's happening there is that all these circle, they never cross in one point. Okay? So they cross in a certain region. Now this region is reflecting the uncertainty of the positioning of the point. It has a name, I don't remember. Okay, so it's the uncertainty region corresponding to the position. Okay, so the way to get this this specific picture, let me say, is that, you know, I can calculate, so I can calculate the a posteriori probability density function for the position given all the estimate of the distance. Okay? So R1, R2, Rn. So my goal is to get the a posteriori PDF of the position given all the estimate of the distance. Given all the distance, actually. Okay? But since the distance are not known, so I can estimate only, then, you know, I need to calculate the a posteriori given the estimate of the distance. Now, the distance are estimated with uncertainty. Okay? So that means that, you know, graphically, when I compound, so I have the a priori and then the conditional probability density function, and the conditional probability density function are, you know, are dependent up to a scaling factor. They are dependent on the true position. Now, you know, these compound in that way, so you multiply. Okay, so you have a, you know, you need to consider as if, let me say, let me try to sketch graphically. That formula is doing the following. So if my uncertainty is Gaussian, that means that if I have my station here, and this is the true range, so it looks like if I have a kind of Gaussians that are, you know, Gaussian distribution that is going this way. Then, if I have another one, at this point, this one has also a Gaussian as well. Then, you know, I have two, let me say, two Gaussian shaped ring. Okay, there are two Gaussian shaped ring. I have a one Gaussian shaped ring, and then, you know, if I have another station here, I have a second Gaussian shaped ring. Now, since I multiply this ring, because looking at the formula, I multiply this ring, so by the multiplication, it comes out that, you know, here is a 0, so I have one ring times 0 is 0. Here I have one ring times 0 is 0, and here I have one ring, here I have one ring times one ring. So, you know, by multiplying here, it comes out that the only non-zero region by multiplication is these 2 points. So when I multiply many, then, you know, when I multiply many of these, then I get this multiplication for that, and this multiplication is similar to those that I illustrate on the other side. So when I multiply, so these multiply with that, so, you know, if this multiply with that, this one is 0 here. So when I multiply these two, I cannot see that part because it's 0. You know, it's 0 this one as well. So, you know, they are all 0 except where they are multiplying one another. Okay, approximately, yeah? Approximately. So this is what comes out by multiplying the 3 uncertainty ring shape. No, but, you know, looking at that formula, and if my a priori is uniform, because I reflect my total ignorance about where is the point, that is the a posteriori. Okay, so this is the probability of my position according to all the measurements, which is R1 and R2 and so on. Okay, so looking at this shape of the a posteriori, this a posteriori is clearly non-Gaussian. Okay, so we are facing that in practical problems like in positioning, we are treating
distributions that are clearly non-Gaussian. You know, by the way, this distribution is changing according to where are the position of the stations and where is the position of the point. Okay? So in positioning, the problem is non-Gaussian, absolutely non-Gaussian. It's non-Gaussian because of the action, so where I move, and it's non-Gaussian because of the geometry, so the assessment of the overall transmitters and receivers. Now, going to the point, you know, the time of delay is linked to the range, to the distance, okay? So the link is between the propagation. So the distance rk, which is estimated rk, is equal to c, which is a propagation, okay? For electromagnetic wave is 3 times 10 to the power 8 meters per second, time tau hat. Tau hat is the time of delay. So, you know, c, just to collect, c is equal to 3 times 10 to the power 8 meters per second for electromagnetic waves, or c equal 335 meters per second is for acoustic on air. Okay? Or, you know, it should be 800 meters per second acoustic into the water. Okay? You know, when you have a sonar, you are estimating position of the target, and that is carried out by the sonar. Now, so going to the point, so you know the range, the distance depends on the time of delay, and the time of delay, we know for the time of delay that the variance of the time of delay is larger or equal than the Kramer-Rao bound. And the Kramer-Rao bound is calculated by, you know, dependent on beta g, where beta g is the effective bandwidth, scaled by SNR 0. The SNR 0 is the signal to noise ratio at the reference distance. So we can say that I calculate the signal to noise ratio at the distance of 1 meter, multiplied by, you know, by rk to r0 to the square, which is, you know, is the signal to noise ratio at the distance, arbitrary distance k. Okay? Now, this is carried out only for convenience, because, you mean, the variance, let me say, this is like to say the variance is equal to beta g times signal to noise ratio at the distance k, okay? And then at the distance k, then, you know, this is just written in such a way that I make the reference to a distance of 0 or 1 meter, and then I scale down to any arbitrary distance. So what I noticed that a part of a beta g, you know, it depends on the waveform. So this beta g depends on the choice of g of t. Okay? And you know, and if I am smart, I try to choose beta g as small as possible. Because choosing beta g as small as possible then makes overall, okay, makes this, the variance to be so small. Now, so this is under my control. For instance, you know, if I'm choosing beta g in satellite system, like in GPS, the choice of beta g is small because I'm using a pseudo-random sequences. And these pseudo-random sequences are designed properly to have this effective bandwidth that is controlled. Now, so going to the point, what is relevant is that the variance of the time delay is depending on the square of the distance. So which means for far away distance, I have a larger delay. So this formula is showing to me that, you know, I mean, if I consider that, you know, my station is here, if I am in this position, my variance is that big. If I'm in this position, my variance is larger. If I'm here, my variance is getting bigger. Okay? So this is what is reflecting that formula. So sitting here, that is my variance sitting there, that is my variance sitting there. That is my variance. So the larger I go, the bigger is the variance. The bigger is the variance, the less informative is the usage of that information about the estimation of that distance. Moving forward. Now, let's estimate the evolution of the point. Now, to estimate the evolution of the point, now I need to discuss that with the formula. Let's look at the geometry of the point. So I have a point. Now I need to concentrate myself on the point. Okay? Now the point is in Rx, and Ry. But the point moves, so the target moves. So since the target moves, then you know the target has a certain speed. Okay? So, you know, the speed of the target, so the vector of the speed is in this direction. So this is the speed at the time n. And the speed at the time n is affected by Vxn and Vyn. So writing, you know, the movement of the target, the movement of the target is Rx at time n plus 1 is equal to Rx at time n, so which means the next position, okay, assume it's here, the next position is the position before plus, you know, is the speed, okay? So it is the speed. What is the speed? The speed is Vxn is the space divided by time. So it's delta Rx divided by delta time. Now let's assume that, you know, our timing is sampled by interval t. So that means that this timing becomes capital T. So, and then this delta Rx is due to the variation this variation is due to the speed. So this one is Vx and time t. So Rxn is equal to Rxn plus 1 is equal to Rxn plus the component of the speed in this direction. But you know, if I make it this way, then you know my position is deterministic. Then it contains a variation about that. And this variation is alpha. Then, you know, what is Ry? I think I didn't use that. Right. Rx is equal to Rx minus 1 plus Vx and minus 1. Oh, Vx is a mismatch because I'm computing x. It's messy. Let me restart it. This point is Rx n minus 1, Ry n minus 1, and I have my speed that is V n minus 1. Okay, now, so my point, so the evolution of the point is This is Vx n minus 1, and the other is Vy n minus 1. Okay. So the next position of the point is Rx n, Ry n. So now I say it again. Rx n is equal to Rx n minus 1, the position where I was, plus Vx n minus 1. I was referring everything to x and make x n plus 1 time t, and Ry n is equal to Ry n minus 1 plus Vy n minus 1 times t. Now, these two are the evolution of the point depending on the speed. Now, who is giving me the speed? I don't know the speed. Then, you know, I need to establish as a speed, okay, that the speed Vx and Vy are updated by a random excitation, which is exciting the speed, so which is making the speed changing. Actually, this excitation is the acceleration. Okay, so which means Vx n is equal to Vx n minus 1 plus alpha x n. And similarly, Vy n is equal to Vy n minus 1 plus alpha y n. Now, these two are the evolution of the speed. The evolution of the speed contains two terms, alpha x, alpha y. So, you know, if I make Vxn minus Vxn minus 1 is equal to alpha n, alpha xn. So alpha is the acceleration. So what I say is that I don't know the acceleration, and I model the acceleration as if it's a random variable. So these random variables represents the excitation of the system. So the position is evolving according to the previous position, plus the speed. And the speed is evolving according to the speed at the iteration before, which is time before, plus the acceleration. Now, you know, I could change, so I can say the acceleration depends on the acceleration to n minus 1 plus an additional term. Now I stop here, and then I say, since I don't know how the acceleration is evolving, so I model these two variables, which represent the acceleration, as the excitation of the evolution of the state. So the state variable, which is indicated there, the state variable are, in this problem, are the position and the speed. Okay? So writing, you know, the state at the iteration or the time n depends on the state at the time n minus 1, which is represented by the position at the time n minus 1, and the speed at the time n minus 1, plus this vector of the excitation. This vector of the excitation contains 0 in the first two positions, because I decide that the excitation is induced by the acceleration. Okay, so, you know, I have the relationship theta n is equal to a theta n minus 1 plus alpha. So these are the linear relationship which is describing the evolution of the state according to the Kalman, as for the Kalman filter model. Now, but you know, what do I measure? you know, what I measure is the estimate of the distance, okay? So what is the relationship between the distance and the position? Now the relationship between the distance and the position is that the distance,
But so the alphas are accelerations.
yeah, which are unknown.
And so shouldn't we have the t's instead of the ones in the A matrices? That would
It's proportional. Okay, it's proportional. I mean, it doesn't change anything if in the second line I put the t, and then you know I put the alpha divided by t.
Oh, okay.
See,
Yeah, it was just
it's a scaling factor. So I mean, you are right. It's not exactly the acceleration. It's the acceleration multiplied by t. Okay, but since t is constant, then you know it's proportional to the acceleration. I correctly say it's not acceleration, it's proportional. It's proportional to the acceleration. Okay? So anyway, but you're right, okay? Now, so fixing that, by the way, you know, I could have stopped by looking at the position and, you know, and add to the position a random term which is representing the speed. So I could have done, I am done, but you know, I could have written I could have said that in case I don't have the speed, you know, like for moving the a pedestrian, because there, I mean, it's important to have speed because perhaps if I'm considering a vehicle that is moving, then you know, having a vehicle that is moving, I know the speed as well. But you know, I mean, if I'm a pedestrian, then I can say that my state equation is Rx, n is equal to Rx n minus 1 plus alpha x n. And Ry n is equal to Ry n minus 1 plus alpha y n. That's another formulation for the state equation. And now the state equation, this is theta n, which is representing the position, not the speed. And then I have this second term is theta n minus 1, and this one is the excitation. And in this case, the excitation is depending on the speed, up to a scaling factor of t. Okay. So I mean, it depends on how many sensors you have. It depends on what kind of sensor you might use. Okay. It depends on the complexity of the model that you want to use. So the model, for instance, in tracking airplanes or missiles or similar device. Now, first of all, in tracking airplanes, you need to use a 3 dimension because the airplane doesn't move in a plane; it moves, you know, with a vertical component. So, if you look at similar equation for describing the Bayesian tracking for objects flying in the sky, then you know the number of variables are Rx, Ry, Rz, which is the position of the point in space. Then you have Vx, Vy, Vz, which is the 3 component of the speed. Now, if you can use also the accelerometer, for instance, you exchange some information between the airplane, the flying object, and the ground, then you can use the accelerometer. Then you put accelerometer X, accelerometer Y, accelerometer Z, okay? Then it comes out that your state equation is composed by 9 variables. This is typical setting for aeronautics, for instance, okay? Because you use 9 variables which are describing the state of the target depending on position, speed, and acceleration. Okay. So now, but you know, so far everything is linear. So I mean, we feel relaxed. Okay. But now, you know, let's see what we measure. So what we measure, you know, remember, in the equation which is describing the evolution of the state, let me write there. So we need to write have. So theta n equal to a theta n plus n minus 1 plus we call alpha. And we have it, is linear. The second one that we have is x n, which is the data, is equal to a function of h that depends on theta n and on beta n, where beta is the noise. And this is the state. This is the most general. Now, what is the data? The data in our case is the data that we collect from estimating the time of delay. So which means every station register the delay, register the signal. So every device transmits a signal which is received by the surrounding stations. Every station receives a signal which is you know, approximate in this way, in time. The signal contains a certain time of delay, which is tau, you know, which is tau k at time n. Okay? But you know, I don't know the time of delay exactly. So I need to estimate the time of delay. So what I do, I estimate my time of delay, tau k. Then I know the relationship between the time of delay and the distance. But since it is estimated, then it's estimated the distance. Okay? So now, this is my information. This is my data. So my data that I'm using for putting here is not the data which is the signature that I measure, but is the data after taking the signature and manipulating it. So the data that I put here, okay, are the set of estimates at the time n. So my goal is, what is the relationship between the states that the data that I measure at the time n with the states that, you know, I collect, it goes into my constituent equation. Now, you know, the state is a position of the target. Okay? So what I do, I need to put a relationship this guy with the other. Now, putting a relationship, it's easy because I know that the distance and the estimated distance is equal to the position of the target minus the position of the station square with Pythagoras, and then it's the position of the target y minus the position of the station y squared. Okay? So by Pythagoras, no, the square root of that plus beta 1. Beta 1 accounts for what? Accounts for the uncertainty on estimating R1. So the variance of the time of delay goes into the variance of beta 1. Beta 1 accounts for the uncertainty on estimating the time of delay. So beta 1, if I know that if the variance of tau and k, okay, is equal to a sigma squared tau k, that depends on the position n. Okay. If I know that, then due to the formula there, I know that the variance of r hat k at the time n and is equal to sigma square tau k n divided by c squared. Now, so this one coincide this is equal to the variance of beta k n, which goes here. Okay? So now you know, I know that what is the variance. I know, so my problem is fully framed because I know what is this variance. But you know, looking at the problem, so looking at the relationship between theta and r, okay, which I can frame in this way. So the set of vectors, so r and n is equal to, so is the norm, the distance is the norm between r n minus r1. In the second position, it is the norm between r n minus r2, where r1, r2, and so on are the receiving station.
But the variance of the range shouldn't be times c squared instead of over c squared. Since the variance of the time of delay is sigma squared, the variance of the range should be.
Let me write it. 1 second. I wait, you know, I write in 1 second. So there might be c squared to multiply. Then you know, I mean, if I have an n station, then you know it's a distance. So it's a normal r n, which is a state, minus r capital N, plus a vector of beta. So beta 1 and beta n. So this relationship, which is putting in relationship the state r, okay, and or at least a piece of the state, because I mean the state contains the position and the speed, is putting a relationship with the state or part of the state with the data according to a non-linear relationship. So this one is non-linear. And this is the noise. Okay. So what we get that, you know, our relationship is now non-linear. So, you know, in our Kalman filter, we need to use a linear relationship. And so, how can you reconcile that? Now, fixing the problem of it. So, my speed is meter per second. And so, if I want to meter, then I multiply, right? Okay. Let's get the coffee and then we continue.